Hi, my name is Taylor Spivey, and in this video I'll be walking you through my ENME 435 LiDAR project. Students this semester were tasked in ENME 435 with creating and using a LiDAR to gather information about a target of their choice. LiDAR stands for light detection and ranging, and it's a way that we remote sense things. Remote sensing is essentially taking and acquiring data on something without physically touching it. And the way we do this largely is by knowing the speed of light, throwing light at something, and then measuring how long it takes to bounce back off something and come back to us. With these parameters, we can calculate the distance it is from us. Using these principles with our LiDAR, we were able to code up a Raspberry Pi in order to do just this. And I will show you that through the rest of this video. The target I selected was this Testudo statue in the LEAP preschool playground. And one of the main reasons I chose it is because I regularly walk by here and I've always looked over and thought it was a cool representation of Testudo, something a little different than the statues. Some interesting characteristics about it are that certain parts are shiny while other parts are more matte. And something that I realized when I was collecting initial data was that I would not be able to get around the back of it as there's not enough room for the LiDAR to work. But this is the target. Here is the fully assembled LiDAR housing. As you can see, it is 3D printed, which we did ourselves, and it is two pieces that then connect through pegs in the middle. You can see that I have my laser here, which is powered by an Arduino Uno. I could very easily just hook that up to my laptop, which made it easy to power the laser. And then over here is the Raspberry Pi. So we have the Raspberry Pi and then the Raspberry Pi camera. Some things that were really important about this design were having the holes match up on each side so that we could firmly secure down both the Raspberry Pi and the Arduino. And also having this little piece that allows us to attach the camera sturdily so that it doesn't move after we do a lot of the calibration. Something else that was really important was assuring that the camera and the laser were exactly 12 inches apart, and that'll come into play here in a second. And the last and final thing was also this area right here, which allowed us to attach a part for potentially using a tripod stand in order to firmly secure and gather our data. Now we'll get into a little bit of the theory on how this works. So, as I said before, we know that it is 12 inches between the camera and the laser. And using that, and then also measuring the angle of how we're scanning, we're able to use triangulation methods along with some calculations in order to calculate the distance from the object to the camera. And through using that, we're able to create X, Y, and Z coordinates that we can then plot on a 3D map. When it comes to measuring the angle, students were tasked with downloading a app on their phones that they could use to essentially detect the angle. And that's what this space on it was for, so that you could lay your phone down and make sure you were at the correct angle that you thought you were. And that is the basics on how the setup works. One thing that was necessary before beginning to gather any data was assuring that the LiDAR was properly calibrated. In the picture of your screen, you can see the first step of this. Students hooked up the LiDAR system, put the laser on the wall, and open up a program that would plot vertical green lines like you see on your screen. The students then had to rotate the laser until the laser line matched up with the green lines. And all this essentially did was make sure that the laser was level in relative to the Pi camera. This was the best way to get accurate data. The second part of the calibration process came from assuring that some of our constants in our formulas were correct. The way we tested this was by setting up our LiDAR and taking pictures, slowly moving back at the same increments and watching the laser get more and more towards the center of the picture. After doing this, we were able to plot that on the curve you see on your screen and compare it to the theoretical curve. So the blue line is a theoretical curve and the actual data is the red dots. What you're seeing here is my data after I have calibrated it. So when it first started, there were red dots. They didn't exactly line up with the blue curve. However, after adjusting some of the constant values, I was able to get it to line up with where we want it. And this was able to complete the calibration and assure that our LiDAR would get accurate results. With the LiDAR calibrated, I was actually able to go out and take some data. So on your screen is a picture of the turtle statue when I was out collecting the data. That would be at an angle of about 0 degrees, and then as I tilt the whole system back a little bit, it would go up by 2 degrees, and I would take another picture. And I would do this for the entire statue, noting down each time the angle that I did it, and the program that I did would account for that and save the picture for me. There were many challenges I incurred while doing this, one being the ambient lighting. Above the turtle, there are some lights, and I think in many ways those lights affected the outcome of this project, as it at times made it hard to see the red laser on the turtle. And also earlier, as I mentioned, some parts of the turtle were more matte while some were more shiny. So certain parts reflected back better than other ones. Another problem was the weather, the week and some change that we had to do this. The weather was not very good, especially at night, which was the best time to take this data. So it was very hard to get out there. I had to go out twice. However, that was about all that I could fit in. But overall, it was a fun experience and we did get something out of it. Here is an example of some of the pictures that we were able to capture when doing the experiment. You can see right here, this is from the front of the statue and at an angle of 0 degrees. That's why there is the 0. Over here, we can see from the left side of the statue, and this is an angle of 12 degrees, which is why there is the 12. And here is from the right side. After collecting all the data, we were able to get X, Y, and Z coordinates in text files. And then we were able to run this MATLAB code, which would inevitably give us the 3D point cloud. So we began off by just importing the data and extracting our X, Y, and Z coordinates from each one. These are from the left, front, and right, as you can see, because we want to essentially get all of these together to create a good 3D point cloud. We then first do some initial plots of our data just to see them, but here is the main part. This is where we actually take the data, and because everything was essentially shot straight on, we have to do this code in order to move it around to make the left side actually go to the left side in the 3D space and the right side actually go to the right side. That way everything isn't in the front. So that is where we do that. And then we color code it by depth and eventually actually plot it. And when we actually plot it, what we end up getting is this. Now, of course, this isn't the best. However, as I talked about earlier, this is largely due because of some of the difficulties that I had recording data. I do, however, think it is important to show this to show that it is not a total failure. The picture you're seeing on your screen is just one side of the data collected, plotted in a 3D space. And I think it kind of shows at the top, you can make out a little bit of the head, and then you can kind of see the body and maybe one leg there on the left. And you can also kind of see maybe where the shoulders for the arms started. So not a total failure. However, I do wish I could have gotten better data. And finally, after taking all 3 of the XYZ coordinates from each of the sides and stitching them into one, we were able to come into the mesh lab and create a mesh of the project. Obviously, because the 3D point cloud did not turn out that well, the mesh cloud didn't either. However, mesh cloud has many benefits. I believe it shows it better in 3D and can more easily translate the 3D. And also the mesh would be able to show a lot of the curvature and stuff such as that had the results been better. But yeah, I hope you learned a lot by watching this video, and I hope you had fun listening, because I know I had fun doing this all through the semester. Thank you.